Okay, let's look at what is kernel self-protection. What is this mechanism and how it helps us in exploring the security options. Kernel self-protection is the design and implementation of systems and structures within the kernel to protect against security flaws in the Linux kernel itself. This covers a wide range of issues, including removing entire classes of bugs, blocking security flaw exploitation methods, and actively detecting attack attempts. The goal for successful self-protecting system would be that they are effective by default, require no opt-in by developers, and have no impact, performance impact, and do not impact kernel debugging and have tests. Well, it is uncommon that all these goals can be met, but it's worth explicitly mentioning them since these aspects need to be explored, dealt with, and to be accepted. So we will look at some of the sub modules on kernel self-protection. What are the ways in which the self-protection can be implemented and how the security flaws can be reduced and attacks can be reduced. So let's look at one by one. What are these? They are like reducing the attack surface, and then reducing the access to system calls and kernel modules, and looking at the memory integrity from such as looking at the stack and the heap overflows, then counter integrity and integer overflows as such. And then we'll look at some of the probabilistic defenses and some randomization of address layout and how we can prevent some information from exposed to the user application. So let's look at one by one at each of these items. Let's start with attack surface reduction. The most fundamental defense against security exploits is to reduce the area of the kernel that can be used to redirect the execution. Like this ranges from limiting the exposed APIs to user space, making in-kernel APIs hard to use indirectly, and minimizing the areas of writable kernel memory. So what we can do is implement a strict kernel memory permissions, such as like when all of the kernel memory, if it is writable, it becomes trivial for the attack to redirect the execution flow. To reduce the availability of these targets, the kernel needs to protect its memory with a tight set of permissions. So executable code and read-only data must not be writable. Like any area of the kernel with executable memory must not be writable. While this obviously includes the kernel code or a text segment itself, we must consider additional places where the executable code must not be writable, such as the kernel module's memory. It should not be writable memory, and same goes with just-in-memory accesses. Well, there are temporary exceptions to this rule to support things like adding breakpoints or keyprobes. So, if in these scenarios, the kernel, if they exist in the kernel, then they should be implemented in a way where the memory is temporarily made writable during the update and then returned back to the original read-only permissions, so that this will help to reduce the attack surface in general. Now, another point, like how this feature has been added in the kernel, that is with the help of this kernel configs, that is config strict kernel read write x and strict module read write x, which seeks to make sure that the code is not writable, data is not executable, and read-only data is neither writable nor executable. And these features are being part of the Linux kernel. Another point is like function pointers and sensitive variables must not be writable. Like as we have seen, like vast area of the kernel memory contain the function pointers that are looked up by the kernel and used to continue the execution flow. Like for example, the descriptors, vector tables, file and network socket, and operation tables and data structures. So those are all being defined with the help of using the function pointers. Many such variables can be made read-only by setting them constant so that they live in the read-only data section instead of data section of the kernel, and getting the protection of the kernel strict memory permissions. So for variables that are initialized once with the directive underscore underscore init time, these can be marked with a new and under development arrow after init attributes. Another point is like we can segregate the kernel memory and user space memory accesses. The kernel must never execute user space memory. The kernel must not also never access user space memory without explicit expectations to do so. Like these rules can be enforced either by the support of the hardware or by the emulation. Like let's look at the hardware support for x86. So x86 provides this feature as supervisor mode access protection. And this is the feature on some of the CPU implementations such as Intel Broadwell microarchitecture that allows supervisor mode program to optionally set user memory mapping so that access to those mappings from the supervisor mode will cause a trap. And this makes it harder for the malicious program to trick the kernel into using instructions or data from the user space programs. And another hardware support is supervisor mode executions, and that is used to prevent supervisor mode from unintentionally executing user space code. And it extends the protection to reads and writes. The support for user mode access prevention is in Linux kernel has been added into the kernel merge 3.7, and it is enabled by default for processes which support this feature. So by blocking the user space memory in this way, execution and data parsing cannot be passed to trivially control user space memory, forcing attacks to operate entirely in the kernel memory as such. So another point is to reduce the access to system calls. So one trivial way to eliminate many system calls for 64-bit systems is built by building the kernel with the config without the config, that is config compact. So this will help to reduce the number of system calls in the kernel that is built, and which is rarely a very feasible scenarios. This is because SECOM system provides an opt-in feature made available to the space, which provides a way to reduce the number of kernel entry points available to the running process. And this limits the breadth of the kernel code that can be reached, possibly reducing the availability of a given bug to an attack. So an area of improvement would be creating viable ways to keep access to things like compact user namespace, BFP creation, and perf limited only to the trusted processes. And this would keep the scope of kernel entry points system calls restricted to a more regular set of normally available to the unprivileged user space. Another option is by restricting the access to the kernel modules. The kernel should never allow an unprivileged user to the ability to load the specific kernel module, since that would provide a facility to unexpectedly extend the available attack surface. For example, like loading a file system module via some unprivileged socket API does not make sense at all. Only the root or physical user, local user should trigger file system module loading. And to protect against even a privileged user, system may need to either disable module loading entirely or might provide assigned modules by the kernel config, such as module sign force, or the kernel system can be configured with LSM modules that support that is the load pin LSM module that keeps from having root arbitrary kernel code via the module loader interface. Now let's look at some of the memory integrity interfaces. There are many memory structures in the kernel that are regularly abused to gain execution control during the attack. By far, the most commonly understood is that of the stack buffer overflow, in which the return address stored on the stack is overwritten. And many applications of this kind of attack exist, and protections exist to defend against them. The classic stack buffer overflow involves writing past the expected end of the variable stored onto the stack, ultimately writing a control value to the stack's frame stored return address. So the user line and the kernel stacks are same in terms of how they function, with a slight difference. For instance, the kernel stack is usually limited to size. For example, on x86, it's like 4K or 8K. And as you can understand, the kernel stack vulnerabilities are not much different from the user line counterpart, and are usually the consequence of writing past the boundaries of the stack allocated buffer. And this situation can occur as a result of using one of the unsafe C functions such as string copy or sprintf, which keep writing to the destination buffer regardless of its size until a null character is found in the source string, or an incorrect termination condition in the loop that populates an array. So let's look at the example of an incorrect termination condition in the loop that populates an array. So here we have an array size of 10, and in this function, the for loop is iterating from 0 to size of an array. Since array elements goes from 0 to array size, when you copy some value into an array with j is equal to 10, we actually writing past the buffer limits and potentially overwriting sensitive memory, that is the pointer saved right after our array. And the most widely used defense is the presence of stack canary between the stack variables and the return address, which is verified just before the function returns. Like one of the kernel configuration, that is config cc stack protector, turns on the stack protector GCC feature. This feature puts at the beginning of the function a canary value on the stack before the return address, and validates the value just before actually returning. And the stack-based overflows override this canary, and which gets detected, and the attack is then neutralized via causing a kernel panic. This way, it ensures this attacks caused by the stack buffer overflow. Another very less understood attack is using a bug that triggers the kernel to consume stack memory with deep function calls or large stack allocations. Like as we've seen, the kernel stack memory is limited, so allocating a large buffer onto the stack can uh, create the security flaws. With this attack, it is possible to write beyond the end of the kernel's pre-allocated stack space and into sensitive kernel structures. Two important changes that might be made for better protection is like moving the kernel thread infrastructure somewhere else and adding faulting memory holes at the bottom of the stack to catch these overflows.